Welcome back to Sleep Science Space, the little corner of the cosmos where we drift through the universe, one slow breath at a time. Tonight we're easing into a question that sounds simple until you actually sit with it. Where does space end? It feels almost childlike, the kind of thing you'd ask while staring at the ceiling late at night. But the deeper you sink into it, the more it stretches your imagination, the way the universe stretches itself. As always, I hope this gentle wander helps you soften into rest, or at least float a little higher above whatever weighed on your mind today. There's always a small chance these ideas might be too captivating and keep you awake, but if that happens, at least your insomnia will come with a cosmic upgrade. Before we drift outward, if you feel like it, a tap on the like button or a quick subscribe helps this tiny, sleepy channel reach more wanderers like you. And I'd love to know where you're listening from. Maybe you're curled up in a warm room in Seoul at midnight, or half awake in Toronto at 4 p.m. on a quiet break. Tell me in the comments. It's always a pleasure seeing this constellation of listeners scattered around the world. Now go ahead and settle in. You don't need to hold on to anything I say. You don't have to focus or stay sharp. Just let the words move through you the way starlight glides through the vacuum, soft and unhurried. And a gentle reminder, this video is only for education and relaxation. It's not medical advice or a substitute for professional help. When you're ready, let's begin drifting toward the question, what is space? That dark ocean we peer into when we lift our eyes at night. What is it made of? Most people imagine space as a simple emptiness, a vast nothingness where planets hang like ornaments and stars sparkle like distant campfires. But the more we learn, the clearer it becomes that space is not empty at all. It's one of the most dynamic, mysterious, and misunderstood features of the entire universe. To understand it, let's rewind the story. For a very long time, humanity imagined space as a silent stage floor, a place where planets and stars performed their motions like actors walking across a wooden platform. This view, shaped by Isaac Newton, treated space as something absolute and fixed a rigid three-dimensional grid that simply existed unchanged while everything else moved across it. Time in Newton's world ticked evenly for all observers like a universal metronome. Space was just the container, constant, unmoving, and then came a man with unkempt hair, a mischievous smile, and equations that would rewrite the universe, Albert Einstein. Einstein shattered that tidy, wooden stage picture of the universe and replaced it with something far more fluid, alive, and quietly astonishing. In his view, space isn't a static backdrop at all. It's a flexible, responsive fabric, something that stretches, curves, and ripples whenever mass or energy passes through it. Space and time aren't two separate ingredients, but threads woven together into a single, four-dimensional tapestry we call space-time. And unlike Newton's silent arena, this fabric reacts. It listens. It moves. A simple way to picture it is to imagine a soft trampoline. Set a heavy bowling ball in the middle, and the surface dips inward. Now roll a marble across it. The marble doesn't travel in a straight line, it arcs around the depression. That gentle bend is gravity in Einstein's universe. We don't fall toward Earth because it's tugging on us like a magnet. We fall because Earth sinks into space time, and we're following the curve it creates. Naturally, you might wonder if space can bend. What happens when there's nothing in it? What about those enormous silent gulfs between stars and galaxies? Surely that must be pure emptiness. But strangely, no. Even the loneliest corners of the cosmos aren't truly empty at all. Thanks to quantum mechanics, we now understand that empty space is still buzzing with activity. At unimaginably tiny scales, space-time is threaded with quantum fields, subtle, invisible oceans that fill the universe. These fields don't live in space. They are space. Every particle you've ever heard of, electrons, photons, quarks, arises from a little disturbance in its corresponding field. And even when no real particles are present, these fields are never perfectly calm. They flicker with tiny fluctuations, producing brief ghost like particles that vanish almost as quickly as they appear. This restless shimmering is called vacuum energy. Think of looking at a pond from far away. It seems still perfectly smooth, but up close the surface trembles with ripples, vibrations, tiny disturbances you couldn't see before. Space is like that, seemingly quiet from afar, but up close alive with motion. Because of this, the vacuum isn't empty, it's potential waiting humming. These virtual particles influence how electrons behave inside atoms. They subtly reshape forces. They may even contribute to what we call dark energy, the mysterious push that's accelerating the universe's expansion. And yes, space itself can stretch, not the galaxies flying apart like shrapnel, but the fabric between them stretching like warm dough. It's a strange idea, but without it, our picture of the cosmos wouldn't make sense. So let's breathe for a moment. I know it's a lot to take in that the emptiest thing in existence is actually a sea of jittering fields, tiny energies, and flexible geometry. But there's a quiet comfort in that idea. It means the universe is never truly silent. Even in the deepest dark, something is always moving. A soft background murmur, a cosmic heartbeat. Space isn't just the emptiness between things, it's a physical entity with temperature, energy, tension, and shape. Even the void between galaxies still holds a faint warmth, just a few degrees above absolute zero relic light from the universe's first moments. So when we ask, what is space? We're asking about one of the universe's most intricate creations. Not a blank canvas, but a living fabric. Not the place where events unfold, but an active participant in the unfolding. It bends, it stretches, it vibrates, it expands. It remembers the Big Bang and carries its echo everywhere. And no, it probably isn't stealing your missing socks. But if they did tumble into a little wrinkle in space-time, at least they'd have an interesting story. Imagine now that you're standing on a quiet hill at night, the air cool, the world still, the stars scattered like ancient lanterns above you. You look up, and the universe feels impossibly vast, stretching out in every direction, soft and endless. But what if I told you that even in this vastness, there's a limit to what your eyes, or any telescope humanity will ever build, can reach a quiet cosmic boundary, not because the universe ends there, but simply because light hasn't arrived yet. Not fiction, not speculation, just the practical, gentle physics of the observable universe. That word observable matters. It doesn't mean that regions beyond don't exist. It means their light, their whispers, their gravitational shivers haven't had enough time to get here since the universe first began to glow. Everything we've ever detected, photons, radio waves, neutrinos, gravitational ripples, they all come from within this cosmic bubble we happen to inhabit. And here's a twist that always makes people blink a little. You might expect this bubble to be about 13.8 billion light years in radius, since that's the age of the universe. But the fabric of space doesn't sit still. It stretches, it grows, it pulls distant galaxies away from us, even as their ancient light travels toward our waiting detectors. Because of that expansion, the farthest objects we can currently see aren't 13.8 billion light years away, they're about 46.5 billion light years out. So, our visible sphere is roughly 93 billion light years across, even though the cosmos itself is only 13.8 billion years old. It's one of those cosmic facts that feels like a riddle until you sit with it gently. A simple picture helps. Imagine setting raisins into a loaf of dough. As the dough rises, every raisin drifts away from every other raisin. Now imagine a beam of light, like a tiny photon, leaving one raisin at the very beginning. By the time that photon reaches another raisin, the dough has expanded dramatically. The distance it traveled wasn't fixed, it was growing the whole time. This is how the universe behaves. Light is fast, but expansion is persistent. From these ingredients, we get the notion of a cosmic horizon, not a barrier, not a wall, more like a fading edge in a deep, starry fog. Beyond that horizon, light simply hasn't completed the journey to us. Not yet. Someday, more of the universe will drift into view. But paradoxically, some parts are drifting away from us so quickly that their light will never reach us. Not now, not in trillions of years. These galaxies aren't breaking any cosmic speed limit. Nothing is moving through space faster than light. Instead, space itself is stretching between us and them faster than light can close the gap. So, in a quiet, almost poetic way, parts of the universe are slipping beyond our eternal reach. But here's something to hold on to, something gentle. Everything you see in the night sky, every star, every soft smear of starlight is within this bubble, the Milky Way, Andromeda, the deep galaxies revealed by the James Webb Telescope. Every one of them sits inside our observable horizon, and each tiny glimmer of light you notice. Some of those photons began their journey long before our Earth even formed. You're catching the faint afterglow of the universe's childhood. Yet, for all its richness, this observable universe may be only a minuscule sliver of the true cosmos. Beyond the horizon, space could continue endlessly flat, curved, folded, or threaded through dimensions we haven't learned to imagine. Those regions exist, but we cannot touch them with light or information. They lie outside the reach of causality itself. What's even more humbling is that every observer anywhere has their own observable universe. If you were standing on a faraway galaxy billions of light years from here, your cosmic bubble would overlap ours partly, but it would also include regions we will never see. In that sense, each viewpoint in the cosmos carries its own private window into reality. So the observable universe is not the universe. It's simply our cosmic view, our temporary bubble of awareness carved out by time and light. And within that bubble, those trillions of galaxies, there's more than enough beauty to last a lifetime, or 1,000 of them. There's a strange kind of comfort hidden inside that cosmic limit, a softness, a reminder that we don't need the entire universe neatly mapped out to feel at home beneath it. Knowing that our vision has boundaries doesn't diminish the cosmos, it grounds us. It reminds us that we're small, local, nestled gently inside one tiny pocket of an enormous reality. And somehow, that makes the stars feel closer, not farther away. Yes, 93 billion light years sounds impossibly huge, and it is, but it's still only the thin, glowing icing on a cosmic cake so vast we can't begin to taste the layers beneath. Whatever lies beyond more galaxies, more filaments of dark matter, or something stranger still, we can only speculate. For now, we drift serenely inside our expanding bubble of light, information, and time. A bubble not defined by borders, but by patience, the patient travel of photons, the slow bloom of cosmic history. It isn't a barrier, it isn't a cage. It's a gift, one that stretches a little farther every day, letting us see deeper into the universe's unfolding story. And here's something tender to hold on to. When we look up at the night sky, we're not seeing the present moment at all. We're peering into ancient chapters, leafing through a cosmic scrapbook made of photons. Every point of light overhead is a message from the past, sometimes the recent past, sometimes the primordial. Take the humble light year. It's not just a distance, it's a time bridge. If a star sits 100 light years away, the glow reaching your eyes tonight left that star a century ago. You're seeing it as it was when your great grandparents were young, when the world you know was still gathering its pieces. Stretch that idea across billions of years. Some galaxies we see tonight began shining toward us before Earth had oceans, before microbes learned to split and multiply, before the sun even formed its first fiery breath. Their photons have been traveling patiently across expanding space, navigating an ever stretching fabric, all so they could arrive gently on your retina or settle quietly onto a telescope's polished mirror. Astronomers call this look back time, the age of the universe at the moment the light started its journey. If a galaxy is 8 billion light years away, you're seeing 8 billion-year-old light. The galaxy you observe is a younger version of itself. The adult galaxy, the one that exists now, may look nothing like the one frozen in your telescope's field of view. It might have merged, changed color, dimmed, brightened, or slipped forever, beyond the reach of our cosmic horizon. In this sense, the universe we see is a museum of light, a fossil record captured not in stone, but in photons. And there is one more quiet twist. As the universe expands, the very light traveling through it stretches like taffy. Its color drifts toward the red end of the spectrum, a phenomenon astronomers call redshift. It's similar to how the wail of a distant siren drops in pitch as it moves away from you, except this shift doesn't come from motion alone, but from space itself swelling between the source and the observer. Since space itself is stretching, nearly every distant galaxy is drifting away from us, and the light they send out gets pulled into longer, softer wavelengths as it travels. That gentle stretching toward the red end of the spectrum is what astronomers call redshift. By studying just how much the light has shifted, scientists can figure out not only how far away a galaxy is, but also how long those ancient photons have been wandering through the cosmos to reach us. A large redshift means we're looking at something incredibly distant and incredibly old. It's like opening a window straight into the universe's childhood. Every red tinted photon is a tiny messenger carrying clues about how fast the universe is expanding, how galaxies grow and transform, and even whispering hints about mysterious forces like dark energy. Light becomes a record keeper, storing memories of the cosmos across unimaginable spans of space and time. This is where telescopes become something quietly magical, not just instruments, but time machines. A small telescope in your backyard shows you nearby worlds as they were minutes or hours ago. A larger one reveals distant galaxies as they appeared hundreds of millions of years in the past, back when life on Earth was still experimenting with simple shapes and shallow seas. And then we have the Titans, Hubble, James Webb, and the next generation of observatories waiting patiently in the wings. These colossal eyes can reach so far across space that they capture the faint glow of the very first galaxies to ever form tiny islands of starlight that came into being only a few 100 million years after the Big Bang. To study the far future of the universe, we end up spending much of our time staring deep into its past. That's simply how the universe works. Light is fast, but the cosmos is vast, and even photons need ages to make the journey. So the universe we see is always slightly outdated, like watching a story unfold with its chapters arriving out of order. Some scenes from nearby cosmic neighborhoods, others from ancient epics when the first stars were just learning to shine. But this delay is a blessing. It lets us gather snapshots of the universe at every stage of its life, laid out across the sky like pages from a fragmented diary. In one direction, we see relatively young galaxies, bright with new stars. In another, we find fragile traces of the earliest cosmic structures emerging from darkness. You could say we live inside a museum built entirely of light, a place where every photon is an artifact from another era, a relic carrying stories across billions of years. The sky becomes a gallery, and the night becomes an archive of everything that has ever glowed. There's a quiet wonder in remembering that every time you look up at the stars, you're looking back in time. The light touching your eyes tonight may have begun its journey long before the earth had oceans, long before the first cell divided, long before our sun even existed. Simply by reading the language of light, its colors, its shifts, its scars, we decode the universe's autobiography. So the next time a star flickers above you, remember you're not seeing it as it exists right now. You're witnessing a preserved moment, a glimmer from a chapter written long ago. Through the patient travel of photons, we continue piecing together our cosmic origin story, one faint glow at a time. To grasp this even more deeply, imagine yourself in a quiet field at dawn. The grass is cool beneath your feet. A thin mist softens everything beyond the nearest trees. You know the world continues, but your vision fades into a gentle blur. That's what our place in the cosmos is like. No matter how powerful our instruments become, there will always be a limit to what we can see, defined not by fog, but by time itself, by distance, and by the restless expansion of space. These limits form what we call cosmic horizons, the shifting invisible boundaries of our observable universe, not the edge of everything, just the edge of what light over the universe's entire lifetime has managed to deliver to us. Unlike the clean, sharp horizon you see on Earth, where the sky melts into the land, the universe gives us horizons of a much stranger, kind, subtle, shifting boundaries that depend on time expansion and the limits of information itself. The first of these is what cosmologists call the particle horizon. Think of it as the farthest edge of the universe from which any signal light gravity or anything else has had enough time to reach us since the moment the cosmos first lit up. It's essentially the outer shell of our observable bubble, the maximum distance our instruments can currently peer into. This horizon is defined not by distance alone, but by age. The universe has been unfolding for about 13.8 billion years, and because space has been stretching the whole time, the most distant light that has finally arrived today comes from regions now roughly 46 billion light years away. That's why our observable universe spans about 93 billion light years across far larger than what you might expect just from the universe's age. But don't imagine this as the rim of a cosmic map or some glowing border with a do not cross sign. There's no surface, no wall, no edge. It's simply the furthest the universe has been able to speak to us so far. Beyond that distance, the light just hasn't had time to get here yet. Next, we drift toward another horizon, one with a slightly more haunting personality. This one is called the cosmic event horizon. It isn't the same as the dramatic kind around a black hole, where even light can't escape a gravitational well. Instead, in cosmology, the event horizon marks the boundary beyond which events will never influence us, no matter how long the universe continues. It's the quiet divide between the regions we can potentially interact with and those we can never reach, now or ever. Because space is expanding. Some galaxies are being carried away from us faster than even light can chase them. Not because they're breaking any cosmic rule, but because the fabric between us is stretching that quickly. It's like tossing a message in a bottle towards someone drifting down a powerful river. You try and try again, but the current pulls them away faster than your message can travel. That's the cosmic event horizon. At this moment, it sits about 16 billion light years away. And here's the bittersweet part. There are galaxies we can still see right now, ancient light, arriving from their past selves, but any new light they emit from this moment onward will never reach us. We're watching them in a kind of cosmic farewell visible today, but destined to slip beyond reach forever. And then there's a broader idea often called the cosmological horizon. Sometimes it's used almost interchangeably with the particle horizon. Other times it refers to any boundary in space-time that limits what we can observe or influence. The details vary depending on the context, but the heart of the concept stays the same. Horizons in the universe aren't just about what we see, they're about the deep structure of space time and expansion. They are boundaries not of matter, but of knowledge limits set by the shape and age of the cosmos. The cosmological horizon is best imagined as a drifting shoreline, a moving edge that marks how far the universe has managed to reveal itself to us so far. As the cosmos ages, that boundary slowly expands, allowing light from more and more distant places to finally wash up on our little island of awareness. These horizons aren't fixed. They shift and evolve as the universe itself changes. The particle horizon stretches outward as time passes because ancient light has had a longer journey to complete. But the event horizon, shaped by dark energy and the accelerating expansion of space-time, becomes increasingly restrictive. More galaxies slip out of reach, not because they disappear, but because the space between us grows too quickly for their light to ever catch up. It's a bit like living on the surface of a gently inflating balloon. The dots far from you drift away faster than the ones nearby. You can only see the ones close enough for their light to make the trip. The rest fade, not because they cease to exist, but because their messages are stretched so thin by expansion that they never arrive. There's something quietly haunting about these limits, a soft reminder that we are not a big cosmic all-seers. Our view is shaped by time distance and the strange elastic nature of the universe itself. We look through a window that is vast, yes, but still bounded. Some regions will remain forever hidden, no matter how advanced our tools become. Not because our telescopes are weak, but because the fabric of space-time places a hard limit on what information can reach us. These unseen places aren't waiting behind a veil to be revealed. Someday they are fundamentally beyond communication. And yet, within these limits, we've learned an astonishing amount. We've charted galaxies across billions of light years. We've measured the faint afterglow of the Big Bang. We've traced the fingerprints of cosmic structure through the fog at the edge of visibility. The horizons don't restrict our imagination, they give it shape. Like morning mist slowly brightening under the rising sun, each new discovery pushes the boundary of the knowable just a little farther. Still, no matter how far we push, some parts will always be hidden beyond the swelling curve where light can never reach us. And yet here we are, drifting quietly through the dark on a tiny world, catching ancient photons as they arrive, listening to the stories they carry, and wondering about the regions we'll never see. Even if pieces of the universe remain forever out of reach, there's beauty in the act of seeking, of following the faint glow of distant light to the edge of understanding, and knowing that being part of this cosmic unfolding is enough. Not too long ago, on the scale of human curiosity, at least the universe was thought to be calm and unchanging. Galaxies simply existed where they were, stars shone where they shone, and the cosmos felt like a grand, steady cathedral. But in the early 20th century, a quiet revolution began on a lonely mountaintop observatory, and it came from a man whose name now floats above Earth on a famous space telescope, Edwin Hubble. When Hubble began studying the faint smudges of distant galaxies, he noticed something quietly astonishing hidden in their light. The farther away a galaxy was, the more its light was stretched toward the red end of the spectrum, a gentle cosmic clue that those galaxies were drifting away from us. And not just drifting, the more distant they were, the faster they receded. It wasn't noise or coincidence or a trick of the telescope. It was a pattern written across the entire sky, a whisper from the universe itself. Space is expanding, but this expansion isn't like galaxies blasting through empty space as if speeding across a racetrack. They're not bullets fired into a cold void. The reality is far stranger and far more graceful. Space, the fabric itself, is stretching, and the galaxies merely ride along, carried like tiny raisins suspended in a rising loaf of bread. Picture that for a moment. The dough is space, the raisins are galaxies. As the dough rises, each raisin finds itself farther from all the others, not because any raisin moved on its own, but because the space between them swelled. No central raisin, no edge, no privileged direction, just a quiet, uniform expansion everywhere at once. This is the cosmos on grand scales. From any galaxy's point of view, ours included, everything else seems to drift away. It's like sitting inside a gently inflating bubble bath. No matter which bubble you occupy, all the others drift outward. Space isn't expanding into something else. It's simply stretching from within. The measuring stick of the universe grows longer, and all distances grow with it. This idea was so revolutionary that even Einstein had to pause. His original equations predicted a dynamic universe, one that could expand or contract, but he was so convinced the cosmos must be static and eternal that he added a cosmological constant to force everything to stay in place. When Hubble revealed the expansion, Einstein muttered that this adjustment was his greatest blunder. Though ironically, that same constant would later return to explain dark energy. In its own subtle way, the universe enjoys its surprises. But the expansion held another secret, a beautiful one. If everything is spreading apart now, then long ago everything must have been closer. Much closer, so close that the entire observable universe once existed in a state of unimaginable density and heat. This realization led to what we now call the Big Bang. The term Big Bang can be misleading. It wasn't an explosion inside space like a firecracker bursting in the darkness. It was space itself swelling from an incredibly compressed state everywhere at once. No center, no blast wave, just the entire cosmic fabric stretching outward from a moment where temperatures and densities were so extreme that the laws of physics as we know them nearly melt. And from that moment forward, galaxies drifted into being. Stars ignited. Space continued to stretch, cooling and calming as it grew. And billions of years later, here, you are listening to a story written into the faint red glow of ancient light. You can't tilt your head toward one corner of the sky and say, There, right there, is where the universe began. Because the beginning wasn't a point in space, it was a beginning of space. The Big Bang didn't burst from a single location. It unfolded everywhere at once, including the exact spot where you're listening right now, and that expansion hasn't stopped. Nearly 14 billion years later, the universe is still stretching, still thinning, still pulling galaxies gently apart. As space expands, the light traveling through it is stretched too, its wavelengths elongated like soft taffy. That's why the farthest galaxies look so red to us. They aren't just distant, they're carried away on an expanding current of space itself. But this grand stretching doesn't tug everything with equal strength. On small scales, stronger forces take over. Gravity binds the Milky Way together. Electromagnetism holds your chair in one solid piece. Even the atoms in your morning coffee cling tightly enough that you don't need to chase your mug across the room. Expansion is something that happens between galaxies, not inside your living room. Your neighborhood isn't ballooning. Your socks aren't drifting toward the edges of the cosmos. At least, probably not. Yet, on the largest scales, the expansion goes on. And here's the twist no one expected: it's speeding up. In the late 1990s, astronomers discovered that distant supernovas weren't behaving the way a slowing universe should. Instead of decelerating, the expansion was accelerating, as though some unseen pressure were pushing galaxies apart faster and faster. That mysterious influence is what we now call dark energy. We don't know what it is. It might be a property of space itself, or a field that hums quietly in the background of everything. But whatever its nature, dark energy currently outweighs all the matter and light we've ever observed. It guides the universe now more than anything else, turning a gentle stretching into a steadily accelerating drift. There's something quietly poetic in that. The cosmos began in unimaginable closeness, every particle pressed together in a brilliant, scorching beginning. Over eons, it expanded, cooled, formed stars, planets, and eventually life. And now it continues to drift outward, like a great story that erupts into motion, grows into complexity, and then relaxes into a slow, endless unfolding. If space could make a sound, which of course it can't, it wouldn't be a deafening bang. It would be something soft, the creak of dough rising, the faint pop of a bubble drifting upward, the slow, warm sigh of something expanding in peace. That is the soundless rhythm of our universe becoming what it is. So when we say the universe is expanding, we aren't imagining galaxies racing away from a single explosion point. We're describing the fabric of reality stretching quietly, steadily, and everywhere like a warm loaf lifting in the dark. It's one of the deepest truths we've discovered, and also one of the most comforting. A reminder that growth doesn't always come in bursts. Sometimes it arrives slowly, gently, beautifully. And as we sit here beneath these quiet stars, wrapped in their fading ancient glow, we're moving with that expansion too. Every inhale you've ever taken, every sleepy blink, every drifting thought has unfolded on a tiny spinning world floating inside a universe that's slowly rising like warm cosmic dough. It's enough to make you curious, or maybe just hungry for a late night snack. In physics, there's a simple rule that seems unshakable. Nothing is supposed to travel faster than light. Not a spacecraft, not a signal, and certainly not your cousin Greg, despite whatever heroic story he tells about sprinting across 6 lanes of traffic back in 2014. Einstein's relativity sets the cosmic speed limit at roughly 299 million meters per second. Anything with mass can approach it, but never quite reach it, let alone surpass it. And yet, when astronomers gaze deep into the universe, they see galaxies drifting away from us at speeds that appear to exceed that very limit. Entire clusters slipping beyond our reach at superluminal rates, as if the cosmos itself forgot to read the rule book. It sounds alarming, but it isn't. Reality is behaving exactly as physics predicts. The trick lies in understanding what exactly is moving. Galaxies aren't zooming through space like bullets. Instead, space itself is stretching, and those galaxies simply ride along the expansion like passengers on a quietly accelerating escalator. Picture a sheet of rubber with tiny dots drawn on it. If you pull the sheet wider, the dots separate, not because they're crawling across the rubber, but because the rubber beneath them is growing. That's how something can seem to recede faster than light, not through motion, but through expansion. The galaxies obey the speed limit. It's the fabric beneath their feet that's doing the work. Another way to picture it, imagine standing on a treadmill that's gradually speeding up. You walk forward, maybe even jog, but the treadmill moves backward even faster. No matter how hard you push, the person at the opposite end drifts farther away. You're not slow. The ground itself is carrying you apart. In the universe, distant galaxies are like that person. Light tries to reach us, but in some regions, space stretches faster than light can travel. The photons never gain ground. They're swept backward by the current. Relativity has no problem with this. Its rule applies to motion through space, not to the growth of space itself. And space, as it turns out, can be surprisingly dramatic when it wants to be. In fact, there was a moment early in the universe's history, cosmic inflation, when space expanded at an absolutely astonishing pace. For a fraction of a second after the Big Bang, the universe ballooned faster than the speed of light by an almost unimaginable factor. In far less than a trillionth of a second, reality grew from smaller than a proton to something the size of a grapefruit, or perhaps even larger, depending on which model you favor. Try writing that into a cookbook, heat oven, prepare ingredients, expand universe exponentially. And again, none of this broke relativity. Nothing raced through space faster than light. It was space itself unfurling in a rapid, silent avalanche of expansion. One of the few times when faster than light behavior isn't forbidden because it isn't movement at all. Just don't try to replicate inflation in a spaceship. Your engines will not be amused. This brief burst of inflation acted like a cosmic smoothing iron, stretching and evening out the young universe before it had time to develop bumps and irregularities. It explains why, even though distant regions have never had the chance to exchange signals or share heat, the sky still looks remarkably uniform in every direction. Inflation didn't just push things apart, it diluted their differences, spreading tiny variations across unfathomable distances. Fast forward to today, and that ancient growth spurt still leaves its fingerprints on the cosmos. Space keeps expanding quietly and steadily, carrying distant galaxies farther and farther from us as the eons roll by. Some of those galaxies now appear to be slipping away faster than light itself, not because they're suddenly flooring the cosmic accelerator, but because the space in between us is stretching more quickly than light can travel. This creates a strange kind of boundary. There are places in the universe whose signals will never reach us, no matter how patient we are. Even if those distant galaxies shine brilliantly, this very moment, their new light is already being swept backwards by the expansion lost to the widening chasm. It's similar to standing on one side of a river while the opposite bank drifts downstream faster than you can throw. You can write as many postcards as you want, none of them will ever reach their destination. Eventually, the idea of sending anything at all becomes meaningless. So, when astronomers say a galaxy is receding faster than light, they don't mean it's breaking the laws of physics. They mean the distance between us is increasing faster than light can bridge. Galaxies follow the rules. It's the carpet beneath them, the fabric of space itself, that's stretching in a way our instincts weren't built to grasp. This leads to an even stranger twist. Some of the galaxies we can still observe, crisp and clear through our best telescopes, have already crossed this unreachable boundary. We see them only because the light they released long ago is still traveling toward us. But any new light they emit today is already too far behind to ever catch up. That new light is gone forever, swept away by the accelerating expansion. It's like watching the red glow of a car's taillights just after it vanishes around a bend. You're seeing the last echo of something that's already moved beyond your path. The glow remains for a moment, but the source is long gone, and there's a quiet sadness to that idea. The universe is full of stories. We'll never hear stars that will never shine in our sky, entire galaxies whose existence we'll only know through ancient whispers. Not because we weren't clever enough or persistent enough, but because the universe itself is gently pulling the edges of the stage farther and farther away. Still, that's what makes our cosmic glimpses so extraordinary. Against all odds, from a small blue planet circling an ordinary star, we've managed to gather light that's been traveling for billions of years. We've studied the shapes of galaxies born when the universe was young. We've captured the faint afterglow of the Big Bang. We've pieced together a story that spans nearly 14 billion years, all while space itself outruns the very light trying to tell that story. It can make you feel tiny, but also profoundly fortunate. Somehow, we're here leaning into the darkness, listening to the faint signals of an expanding universe, watching galaxies drift into the distance like lanterns carried away by a silent tide. And above us, the dough of the cosmos keeps rising, stretching reality outward, while curious minds below wonder how far the light can travel. When we imagine the universe, it's easy to picture it as a giant dark container. When we picture space, most of us imagine a giant rectangular box floating in the void, something with a top and bottom, a left and right, like a cosmic storage container holding galaxies. Maybe there's an edge somewhere out there. Maybe an enormous wall with a faded "Do Not Enter" sign guarded by a very sleepy cosmic employee. But the true shape of space is far more subtle and far more elegant than anything our intuition tries to draw. Space might not be flat, the way a sheet of paper is flat. It might curve, it might arch inward or stretch outward, or it might be so gently flat that from our vantage point it feels perfectly straight. And this isn't just a mathematical curiosity. The geometry of the universe shapes everything from how galaxies form to how the cosmos might end billions of years from now. To explore this, let's drift slowly through the three main possibilities. The first shape is a flat universe. Imagine an endless plane, smooth and infinite. In this kind of geometry, the rules from your school geometry class work just fine. Parallel lines stay parallel forever. Triangles behave themselves and add neatly to 180 degrees. And if you traveled in a perfectly straight line, you'd just keep going, no looping, no curving back around, just an endless glide through limitless space. The second possibility is a closed universe. Instead of being flat, space might wrap around on itself like the three-dimensional cousin of a sphere. In that kind of cosmos, heading straight doesn't take you outward forever. It eventually leads you right back to where you began. A very long cosmic loop. Just like walking around Earth, you never reach an edge because there is no edge. You simply return full circle, though it would take longer than any lifetime has room for. The third option is an open universe. This one curves the opposite way, like the shape of a saddle or a gently arched Pringle. Lines that start parallel eventually drift apart. Triangles add up to less than 180 degrees, and no matter how far you travel, you'll never find yourself looping back home. This geometry opens endlessly outward. These shapes aren't random guesses. They're directly connected to how much matter and energy the universe contains. Specifically, the total density of everything matter. Radiation, dark energy, compared to a special critical value. Too much density and the universe curves inward. Too little and it curves outward. And if the density is perfectly balanced, space stays flat. It's the Goldilocks equation of cosmology, not too heavy, not too light, just precisely tuned. But how do we measure something so enormous? We look at the oldest light in existence, the cosmic microwave background, the faint afterglow left behind from the early universe. This ancient radiation carries tiny ripples, subtle variations, like wrinkles on a cooling surface. By studying how those ripples spread across the sky, scientists can infer the curvature of space itself. And the answer so far is astonishing. All evidence points to a universe that's extremely close to flat. Not perfectly flat in the strict mathematical sense, perhaps, but flat enough that any curvature is too gentle for our instruments to detect. Like standing on a huge plane that might curve ever so slightly far beyond the horizon, but from where you're standing, it's smooth as glass. And here's where things become quietly mind-bending. Even a flat universe might be infinite, or it might not be. Meanwhile, a closed universe can be finite, but without any boundaries. That phrase, finite but unbounded, sounds contradictory at first, like a cup that's full but holds no liquid. But it's easier to visualize than it seems. Think of the surface of a sphere. You can measure its total area. It's finite, but it doesn't have an edge. You can wander across that surface forever and never reach a border because the surface loops back on itself. Now, stretch that idea into 3 dimensions, and you get a universe that's self contained. No edges, no walls, no outside. Just a smooth cosmic space bending gently back onto itself in a way you and I could never perceive. From inside, it traveling straight feels ordinary. You just keep going unaware that the road you're on curves subtly through a universe that is quietly folding back around you, while quietly curving back toward its own beginning. Even in a universe that's flat or open infinity has its own gentle strangeness. If space truly stretches without end, then the number of galaxies is not just enormous, it's unbounded. Infinite stars, infinite worlds, and perhaps tucked unimaginably far away versions of familiar patterns repeating themselves. In an unlimited cosmos, there could be a distant place where someone remarkably similar to you is curled up listening to something just like this, maybe wearing a different pair of pajamas or drifting off in a slightly different room. Of course, this is speculation wrapped in mathematics, because beyond our observable horizon, we simply have no access to what space is doing. It might go on forever. It might bend gently into a loop far larger than we can measure. The curvature might be so subtle that even a beam of light traveling for billions of years wouldn't reveal any hint of bending. It's like standing in a quiet meadow trying to decide if the earth is round. From where you stand, everything looks perfectly flat, but the truth only reveals itself on scales far grander than your view allows. And this cosmic geometry does more than describe shape, it influences destiny. In a closed universe, gravity might one day tug hard enough to overcome expansion, slowly gathering everything back together in a long, deep contraction. A reverse unfolding of time, ending in a big crunch, but in a flat or open universe, especially one propelled by dark energy expansion, likely continues without end. Galaxies drift farther apart, stars burn out matter, thins, and the cosmos cools into a soft, peaceful, dimming hush. With the current evidence, this quiet, ever expanding future seems the most probable. Still, in a curious way, the shape hardly matters. Whatever the universe turns out to be, curved inward, curved outward, or perfectly balanced, we belong to it. Your atoms move according to its geometry. Your heartbeat unfolds in its space time. Your thoughts and memories shimmer in the same fabric that guides galaxies. We aren't simply living inside space, we are made of it. Little knots of cosmic material shaped by the same equations that sculpt the stars. So, if the universe is flat, we drift across a vast open sheet of possibility. If it's closed, we're traveling inside a 3 dimensional loop with no edge. If it's open, we're gliding across an endless cosmic saddle, carried outward with no return path needed. Whichever version is true, each is beautiful in its own gentle way. You don't need to decide which shape you prefer to feel the wonder of it. You can simply look up on a clear night, notice the stars keeping silent company, and remember that you're standing on a tiny patch of a universe whose full outline we're still patiently trying to sketch from within. And to make that feeling more vivid, imagine this. You're a tiny creature living on the surface of a balloon. You can walk north, south, east, or west across its curved skin, but you can't tunnel inward or climb outward. Your entire world is that smooth, seamless surface, curved finite, and completely without edges. You wouldn't know that the balloon you're walking on is being pinched between the fingers of some imaginary cosmic toddler with a helium tank. All you'd ever notice is that when you stroll straight ahead, eventually, mysteriously, you end up back at your starting point. That's the quiet charm of curved space. It bends reality in ways that don't match the logic of everyday life, yet it becomes surprisingly natural once your mind settles into its rhythm. And even though we humans move around in 3 dimensions, 2 dimensional curved surfaces give us a gentle doorway into imagining how our universe might behave on a scale far beyond our experience. Let's start at the simplest level. On a flat plane, like the surface of your desk or a smooth sheet of paper, geometry follows the rules we learn in school. A triangle's angles always add neatly to 180 degrees. Parallel lines stay the same distance apart forever. And if you head straight in one direction, you'll keep going indefinitely unless you hit an obstacle or perhaps the edge of the table. But shift your attention to the surface of a sphere, a planet, or the outside of that balloon, and the rules begin to loosen. Draw a triangle using great circles, and the angles sum to more than 180 degrees. Lines that start parallel eventually cross or diverge. And if you walk straight long enough without turning even once, you'll find yourself back where you began. No cliffs, no edges, just a seamless loop. From the viewpoint of a creature living on that surface, the world feels endless. But in truth, it's finite, simply curved in a way that keeps you from ever reaching a boundary. Now, stretch that concept upward into a 3 dimensional version. Imagine that our entire cosmos is like the surface of that balloon, except instead of curving in 2 directions, it curves in 3 or perhaps 4 or even dimensions we can't easily picture. We aren't floating outside the balloon looking in. We're inside the geometry itself, immersed in it, unable to step out and peek at the shape from afar. In this analogy, galaxies are like specks of ink on the balloon's skin. As the balloon inflates, the specks separate. They're not crawling away under their own power space. Between them is stretching. That's what cosmologists mean by expansion, not motion through space, but the growth of space itself. And if space really does fold back on itself, then traveling in a perfectly straight line long enough could, in principle, lead you back home. You wouldn't encounter a cosmic border or an end of the map. Space would wrap around smoothly, an elegant loop without a wall. A finite universe with no boundary is one of those ideas that feels impossible at first glance, yet becomes almost soothing when you sit with it. You could wander forever inside a space that technically has a limited size, and you'd never reach an edge because there isn't one. This balloon model also reveals another subtle truth. There is no special center of the universe. On the balloon's surface, there's no preferred point from which expansion radiates. Pick any spot and call it here, and the expansion will look the same in every direction. The universe behaves the same way. There's no cosmic bullseye, no privileged location. Everywhere is equally central, but as with all analogies, there are limitations. The balloon's surface exists inside of a higher dimensional space you can visualize. Our universe, if it curves, may be bending in a higher dimensional direction we cannot perceive at all. It's not floating in an external void. It doesn't need an outside to bend. Space can curve, intrinsically shaping itself by its own rules independent of any surrounding medium. In that sense, the balloon is just a whisper of the real idea, a gentle doorway into something far more subtle and breathtaking. This idea of intrinsic curvature is one of Einstein's quiet revolutions. In his vision space and space-time as a whole isn't a blank platform waiting for the universe to perform on top of it. It's an active participant, a living geometry with its own texture and behavior. Mass and energy shape space-time, and in return, the curvature of space-time guides the movement of matter. It's a kind of cosmic reciprocity, a looping dialogue that governs the fall of an apple, the orbit of the moon, the swirl of galaxies. And this curvature doesn't just steer planets, it steers light itself. In a curved cosmos, light doesn't travel in the straight lines our intuition imagines. It follows geodesics, the shortest possible paths through a bent landscape. On a sphere, that path is a great circle. In our universe, it's a smooth arc molded by gravity and the underlying shape of space-time. That's why massive bodies like galaxies and black holes can bend and distort light, producing phenomena like gravitational lensing. When we look out at the stars, we're not simply seeing a scatter of points against an empty canvas. We're watching light weave through a contoured universe, stretched and curved by everything it encounters. It's a bit like looking through a slow, glassy funhouse mirror, only the distortions reveal the truth. And now back to our balloon one last time. As it inflates, the dots drawn on its surface drift apart, but the dots themselves don't swell. The balloon stretches between them, not within them. That's how cosmic expansion works. It applies only on enormous scales between clusters of galaxies. Anything held together by gravity or atomic forces stays the same size. The Milky Way isn't being pulled like taffy. Your coffee mug isn't enlarging. The expansion only lives in the great cosmic voids. What's causing that expansion to accelerate is something even stranger: dark energy. A mysterious form of energy woven into the fabric of space, pushing everything apart with increasing speed. It's as if someone keeps adding extra pressure to the balloon, causing it to grow more vigorously with each passing moment. We don't know what dark energy truly is, but we can feel its footprint in the way distant galaxies drift away and in the way ancient light spreads across the sky. So, where does all this leave us? It means we inhabit a universe that may be subtly curved, finite, but without boundaries, centerless, yet expanding, shaped by rules that rarely match our everyday intuition, but make perfect sense in the grand geometry of it all. And astonishingly, a simple balloon captures the essence of this cosmic architecture, a modest rubber model floating through our imagination, whispering clues about how reality might be stitched. The next time you see a balloon drifting upward, you might give it a quiet nod. Yes, it's filled with helium and childhood memories, but hidden inside the shape are echoes of the universe itself, a soft curve, a stretch of space, and the gentle suggestion that the path ahead and the place you began may someday meet again after a long journey around the cosmos. Now, let's step into a grander question, one that always feels as if it should be spoken in a whisper infinity. The word alone feels vast, heavy, as if it opens a door into something too large to comfortably hold in the human mind. We imagine infinite stars, infinite galaxies, infinite space, endless and unbroken. But what does it actually mean to ask if the universe is infinite? So far, everything we've measured about the large scale cosmos hints that it might be. Observations of the cosmic microwave background, the faint ancient glow still ringing through the universe, suggest that space is very nearly flat, not spherical, not saddle shaped, but astonishingly straight in a geometric sense. And in general relativity, a flat universe can extend forever. If it doesn't, then whatever lies beyond our sight must still be vastly larger than our cosmic horizon. That brings us to the observable universe, the glowing bubble we can actually detect. It stretches about 93 billion light years across. That's the portion of the cosmos whose light has had time to reach us. Beyond that, space may continue indefinitely. There may be realms filled with galaxies. We will never glimpse regions forever hidden behind the limits of light and time. And here's the humbling part: we cannot prove or disprove whether the universe is infinite. Our instruments, our telescopes, our theories, none of them let us peek past the ultimate horizon. We're like tiny creatures on a wide beach. Look left, right, forward, backward. All you see is sand. It might stretch across continents, or it might end just beyond the dunes. We simply can't see far enough to know. This brings us to something subtle but important. When we talk about infinity, we're not talking about a measurement the way we talk about the distance to the moon or the height of a mountain. There's no cosmic ruler we can extend outward until the marks run out. Infinity isn't a number. It's a concept, an idea our minds use to describe something that has no natural stopping point. And in science, ideas only become meaningful when there's evidence to support them. That's where the challenge lies. You can never directly observe infinity. You can only look for hints that space doesn't curve back inward, doesn't show signs of looping, and doesn't reveal any kind of cosmic boundary. So far, every direction we look in shows more universe, more galaxies, more structure, no edge, no abrupt ending, no cosmic cliff to fall off. But that doesn't prove an edge isn't out there, somewhere beyond the reach of light. It simply means we lack the ability to see far enough to know. And unless someone invents a telescope capable of outrunning light itself and outrunning the expansion of space, we'll always be peering through a limited window. The idea of an infinite universe leads to consequences that are strange, beautiful, and faintly dizzying. If space truly stretches on without end, then the amount of matter scattered through it is also unending, or at least so vast that it behaves that way. That means uncountable stars, uncountable planets, uncountable possibilities. Somewhere far beyond any horizon we could ever access, there might be another world with mountains that glow, oceans that hum, or forests shaped in ways our imaginations haven't learned to picture. And somewhere deeper in that cosmic vastness, life may have risen. Perhaps it wonders the same thing we do, where the universe ends and whether it ends at all. Then comes the truly mind bending part. In an infinite universe, if matter is distributed roughly evenly, then probability says patterns will eventually repeat. That means there could be another version of you far, far away, so distant that its light will never reach us, not even if we waited forever. Maybe that version made slightly different choices this morning. Maybe it put sugar in its coffee instead of leaving it black. Maybe it chose a different path years ago. The possibilities multiply quietly, endlessly. But don't worry, you're not going to meet your cosmic twin in the grocery store aisle. These regions are so distant, so unreachable, that they might as well exist in a separate reality entirely. Their light will never touch our eyes. Their stories will never cross into our sky. Infinity isn't just about size, it's a shift in perspective. It turns the universe from something enormous into something without borders. There's no edge to imagine, no wall waiting beyond the last galaxy. Just more space, more structure, more possibilities stretching out without a final page. Still, scientists remain cautious. We only have access to a limited cosmic sample, the observable universe. It's entirely possible that the true universe is very large, but still finite, curving gently back on itself in a way we're too small to detect. It might fold through higher dimensions or form a shape stranger than anything our imagination has rehearsed. There's also the matter of time. The universe may be endless in extent, but not eternal in age. It had a beginning, what we call the Big Bang, and whatever existed before that moment remains hidden behind the limits of our theories. Even an infinite cosmos has a history, a timeline, and unfolding. Philosophically, infinity pushes against the way we're used to thinking. Everything familiar to us has boundaries, our days, our energy, the number of cookies we allow ourselves before bedtime. Infinity removes those boundaries. It lifts the ceiling entirely. For some, that's exhilarating. For others, a little overwhelming. Even ancient thinkers wrestled with this idea. Aristotle argued the universe must be finite because actual infinities felt too strange to accept, and even today, physicists and philosophers debate whether a true physical infinity exists or whether it's simply a useful mathematical tool the universe approximates but never fully embodies. Either way, infinity invites us into a gentler truth, one that doesn't demand certainty. We don't need to know whether the universe ends somewhere far beyond the last galaxy. We simply need to know that the part we can see already offers enough wonder to last a lifetime. The rest, whatever it is, waits quietly in the dark, humming softly beyond the reach of light. Whether the universe stretches endlessly or eventually curves back on itself, simply thinking about it does something powerful. It widens the mind, softens the ego, and gently reminds us how tiny our viewpoint really is. Every time you look up at the night sky, you're glimpsing a mystery so vast that even our most ambitious measurements barely skim its surface. You're seeing a handful of glowing specks, a few windows illuminated in the grand mansion of the cosmos. And yet here we are, small beings, on a drifting world, asking how far space goes. We design telescopes to chase ancient starlight. We invent mathematics to describe what we can't reach. And sometimes, when the house is quiet and the night feels wide, we lie awake, wondering what exists beyond the last flicker of light our detectors can capture. Maybe the universe goes on forever. Maybe it has a shape that eventually closes in on itself. Either way, it's more than enough. Enough to inspire curiosity, to spark imagination, to fill science with questions, and to give our dreams a place to wander. You don't need to know its true extent to feel at home within it. You're already woven into its fabric, a momentary glow on the frontier of the observable shining gently inside a cosmos that might have no end at all. There's something magnetic about the idea of an edge. We grow up surrounded by endings, walls, fences, roads, tabletops, doorways. Everything we touch has a boundary, so it feels natural to assume the universe must have one too. Surely, after traveling an impossible distance, space must stop. Maybe like the final hallway in an enormous house, or the edge of a giant cosmic platform overlooking nothing. But the universe plays by different rules. Space doesn't require an edge. It can be limited in size without having a boundary at all, and that's where things become beautifully strange. Start with something familiar. Imagine standing on Earth and walking in a straight line. No matter which direction you choose, you'll eventually end up right back where you began. You never fall off. You never find a wall or a warning sign telling you to turn around. The surface is finite, but it has no edge. It folds smoothly into itself. Now stretch that idea from a two-dimensional surface to a three-dimensional realm. Picture a volume of space that loops back in every direction. If you could travel in a perfectly straight line through this kind of universe, no detours, no obstacles, you might eventually return to your starting point, having never encountered a border or a drop-off. A cosmos that's finite, yet boundaryless, self-contained, smooth, continuous, and from the inside living within it, you'd never be able to spot the loop directly. To you, every direction would look like it goes on forever. No edge, no outside, no end, just space, curving quietly into itself while you move through it, unaware you're tracing the outline of a cosmic circle. This kind of space isn't a fantasy from science fiction. In modern cosmology, it's a completely legitimate way the universe might be structured. Scientists call it a finite but unbounded space. At first, the phrase sounds contradictory, almost like saying a cup can be full without holding any liquid. But once you grasp the geometry behind it, the idea becomes surprisingly intuitive. Space can curve in on itself, forming a complete volume without ever needing to stop or border anything. A classic tool for imagining this is the torus, the simple shape of a donut. Not the kind filled with jelly, but the smooth ring with a hollow center. The surface of that donut is two-dimensional. An ant wandering across it could roam indefinitely without ever falling off or meeting an edge. That surface loops back on itself horizontally and vertically. Every direction leads somewhere, and eventually it leads back home. Now lift that idea into a higher dimension. Picture a three-dimensional version of such a looping structure where space folds through itself in ways our intuition struggles to picture. The universe doesn't have to look like a pastry, of course, but the torus gives us a gentle metaphor, a cosmos where you could travel perfectly straight for an unimaginably long time and eventually arrive exactly where you began, as if space itself had quietly wrapped around behind you. Another friendly analogy comes from early video games. In classics like Pac Man or asteroids, moving off the right side of the screen instantly brings you back on the left. There's no wall, no barrier, you simply loop around on a map that wraps seamlessly. These game worlds are finite, but their boundaries behave more like connections than fences. They're simple 2D hints of what a looping topology could look like on a cosmic scale. In theoretical cosmology, this isn't just a playful idea. Some models genuinely suggest that the universe could possess a repeating structure, a topology with built in loops. If that were the case, certain patterns in the cosmic microwave background, the ancient afterglow of the Big Bang, might show faint repeated signatures like subtle reflections in distant wallpaper. So far, we haven't detected any clear repetitions, but the possibility hasn't been fully eliminated. The deeper truth is this: the universe doesn't require an outer surface or some surrounding emptiness. That's a human expectation shaped by living in a world where objects sit inside bigger objects, rooms, inside houses, houses on land, land on a planet. In reality, space isn't sitting inside anything. It is the container. It doesn't need an outside to curve or a border to feel complete, just as the surface of a globe needs no edge to exist. Even if the universe turns out to be infinite, that doesn't imply there must be a final boundary out there somewhere. Infinity isn't a location, it's a property. Saying that space might be infinite is like saying numbers never run out. You don't have to find the last number to understand that one doesn't exist. Likewise, you don't have to locate the edge of the cosmos to accept the possibility that there may be no edge at all. Edges create their own philosophical puzzles. If space suddenly ended, what would lie beyond? More space waiting quietly in the dark. Something entirely different, a blank nothingness that stubbornly resists definition. The questions multiply, each one stranger than the last. And perhaps that's the most elegant clue of all: the simplest way for the universe to avoid an impossible boundary is to not have one in the first place. This kind of space isn't the stuff of sci-fi daydreams. In modern cosmology, it's a perfectly reasonable way the universe might be shaped. Physicists call it finite, but unbounded, a phrase that sounds contradictory at first, almost like claiming a cup can be full without actually containing anything. But once you sit with the geometry for a moment, the idea settles into place. Space can fold in on itself, forming a complete volume without ever needing to stop, end, or run into a boundary. A simple way to picture this is with a torus, the familiar donut shape. Not the sugary kind with filling, but the smooth ring with a hollow center. Its surface is two-dimensional, and if you imagine a tiny ant wandering across it, that little traveler could roam forever without ever falling off an edge. The surface wraps around on itself, both horizontally and vertically, creating a world where every direction eventually loops back home. Now lift that concept into three dimensions. Imagine a space where the looping happens not across a surface, but throughout the volume itself, folding and reconnecting in ways that are hard for our everyday intuition to grasp. The universe doesn't need to resemble a pastry, of course, but the torus gives us a gentle metaphor, a cosmos where you could move in a perfectly straight line for unimaginable distances and eventually arrive at your starting point as though space had quietly curved behind your back the entire time. A more playful analogy comes from classic arcade games. In old favorites like Pac-Man, or asteroids moving off one side of the screen makes you pop back in from the opposite side. There are no walls, just seamless connections. The map is limited in size, but it doesn't behave like a box. It loops. Those games give us a small, two-dimensional hint of what a looping universe might feel like. In actual cosmology, this isn't just a fun thought experiment. Some models genuinely propose that the universe may have a repeating topology, a built in pattern that connects distant regions. If that were true, we might expect to see subtle repetitions in the cosmic microwave background, the faint, ancient glow left from the Big Bang, as if distant patches of sky were mirror images of each other across the fabric of space. So far, nothing conclusive has shown up, but the idea remains open. The deeper point is that the universe doesn't need an outside or an edge. Our human instincts expect borders because we're used to objects sitting inside larger objects, cups in cabinets, buildings on streets, planets in space. But space itself isn't inside anything. It is the medium. It doesn't need a surrounding container to curve, stretch, or feel whole. Just as the surface of a globe needs no physical edge to exist, space can be complete without a boundary. And even if the universe turns out to be infinite, that doesn't mean there's some distant border we haven't reached yet. Infinity isn't a destination, it's a property. When we say numbers go on forever, we don't look for the final number. We simply understand that there isn't one. In the same way, we don't need to locate the edge of the universe to accept that there may not be an edge at all. Whenever we imagine a boundary, we're forced to ask awkward questions. If space seeped what would sit beyond that stopping point, more space, nothingness, something we don't have language for. Each possibility creates more puzzles than it solves. And maybe that's the quiet hint nature gives us. The simplest way to avoid the impossible question of what lies beyond the edge is for there to be no edge at all. But even though you can't see it, that ancient glow is still here, quietly filling every corner of your room right now, drifting through the walls. Your pillow, the air around you, like a soft, invisible breeze that began its journey at the dawn of time. The discovery of this glow, the cosmic microwave background, was almost accidental. Back in the 1960s, two radio astronomers, Arno Penzias and Robert Wilson, were testing a large horn shaped antenna. No matter where they pointed it, they kept picking up a stubborn hiss, a faint background signal that simply wouldn't go away. They cleaned the equipment, recalibrated everything, even shooed away a pair of pigeons that had taken up residence in the antenna. But the hiss remained. Constant, uniform, unmistakably cosmic. What they had stumbled into without initially realizing it was the afterglow of the Big Bang, the leftover radiation filling all of space. A whisper from the infant universe, a signal that theory predicted now found in plain static. Since that moment, scientists have mapped this faint radiation with exquisite precision. Space missions like COBE WMAP and the more advanced Planck satellite have given us detailed portraits of this ancient light. And in those maps, we find more than just a glow, we find a record, a blueprint, a snapshot of the universe at less than 380,000 years old. At first glance, the cosmic background looks almost perfectly smooth, the same temperature in every direction. But when you zoom in, tiny variations appear, microscopic warm and cool patches differing by only a few millionths of a degree. And these tiny ripples are the origin of everything. They are the first seeds of structure, slight differences in density that over billions of years would grow into galaxies, stars, planets, and eventually into you lying in bed, now listening to a quiet story about the cosmos. These temperature ripples are clues. They tell us how matter was arranged in the early universe. They let us test ideas about how space expanded, how time unfolded, and how the first cosmic structures took shape. Even the geometry of the universe leaves subtle fingerprints in this ancient light. If space were curved like a sphere or a saddle, or perfectly flat, those shapes would influence the way the ripples appear. By studying the size and distribution of the fluctuations, cosmologists can infer the overall shape of the cosmos. And so far, within the limits of what we can measure, the universe appears astonishingly close to flat. It's a bit like watching ripples on a pond to learn the shape of the shoreline. The way waves stretch, scatter, and echo carries information about the environment around them. In the same way, the cosmic background carries encoded messages about the vast structure of space. Light becomes data, photons become historians, and somehow that idea is soothing. This ancient glow drifting all around us, not bright or harsh, but soft, steady, a quiet warmth woven into the fabric of reality itself. If you had the right kind of radio receiver, you could hear it anywhere, not as music or melody, but as a faint universal static, a gentle hiss left over from a time when the universe was young, hot, and glowing. It's the closest thing we have to a baby picture of the cosmos, a snapshot preserved across 13.8 billion years of expansion. That light has outlived countless generations of stars. It has crossed distances so vast that our language barely contains them. And after all that time, all that travel, it's arrived here in your lifetime, ready to be measured, mapped, and understood. In a universe filled with mystery, the cosmic microwave background is something steady and comforting, a piece of evidence, a relic we can actually touch with our instruments, a reminder that we don't need to find the physical edge of space to uncover its beginnings. Some answers are already drifting around us, waiting in the background glow. So the next time you step outside at night, try imagining the darkness as something not empty, but softly lit by an ancient invisible radiance. Light that has traveled for more than 13 billion years. Light that has stretched and thinned with the expansion of space, but still endures. A quiet record of everything that ever was woven into the silence. And with that thought, we arrive gently at the next question, one that has puzzled astronomers and dreamers alike. Is there truly an edge to the universe? A final frontier, some boundary, where space itself comes to a stop? While most of modern cosmology leans toward a universe with no sharp boundary, a few more speculative ideas open a quiet doorway to stranger possibilities, places where edges might exist, even if they're nothing like the borders we imagine. These aren't mainstream conclusions, but gentle thought experiments that help stretch the mind a little further into the dark. One of the most intriguing comes from certain versions of string theory, the idea that our entire universe could be a kind of three-dimensional membrane called a brain floating inside a larger, higher dimensional environment. In this picture, everything we touch or see is confined to this cosmic membrane, like tiny creatures living on the skin of a soap bubble. All the familiar particles and forces are trapped here, except gravity. Gravity may have the freedom to leak into the surrounding higher dimensional space, which is one reason some physicists suspect it feels so weak compared to the other forces. If this brain world view is right, then the universe might have a sort of boundary, but not a wall we could ever reach. The edge would exist in the higher dimensions we cannot access or sense. From our three-dimensional perspective, everything appears smooth and endless. But to a hypothetical five-dimensional being with a wider view, our universe might look like a cosmic sheet with a subtle outline. It's a dizzying thought to imagine that something with more dimensions than we can comprehend might see our cosmos the way we see a page in a book. But in a strange way, it's comforting too. We would be the mysterious ones to them. Another exotic idea involves something called cosmic domain walls. These would be the boundaries separating regions of space that settled into different states in the early universe. Imagine the cosmos cooling after the Big Bang, the way water freezes into ice, but freezing imperfectly patches, forming with slightly different settings for the laws of physics. Where these patches meet a vast invisible wall could form. Most models predict that if these ever existed, they would have faded into near nothingness very early on. But in more speculative scenarios, a few could remain silent, enormous stretching across unimaginable distances. Crossing such a boundary wouldn't necessarily be dramatic. You might step through it without noticing, except perhaps for some subtle change in how particles behave. Maybe your atoms would shift ever so slightly. Maybe your tea would taste a bit different for reasons you couldn't quite explain. A barely perceptible change in the underlying rules. Then there's the bubble universe idea from eternal inflation. In this model, the early universe wasn't just expanding, it was frothing like boiling water. Tiny regions stopped inflating at different times, forming self contained bubbles of space, each with its own laws of physics, its own constants, its own cosmic personality. Our universe would be one bubble among many drifting in a vast inflationary sea. If that's the case, then yes, our bubble has an edge, an interface between our region of space-time and the inflationary background outside. But it's not an edge we could ever reach. Even if other bubbles exist, they're so distant that the light from them will never touch us. Collisions between bubbles are theoretically possible, but unbelievably rare. We may be alone in our little cosmic sphere, floating quietly in a foam of other universes. And then there's Gödel's universe, one of the strangest solutions ever written to Einstein's equations. Kurt Gödel, famous for shaking mathematics with his incompleteness theorems, proposed a rotating universe. Not galaxies spinning independently, but the entire fabric of space-time, twisting slowly as a whole. In such a cosmos, time takes on a strange bend. Certain paths through space-time would loop back into their own past. In other words, a universe where time travel isn't impossible, but simply part of the geometry. It's not a model that matches our observations, but the idea is hypnotic, a cosmos where edge and beginning blur, and where following a certain trail through space would quietly bring you back to a moment you already lived. All these possibilities, from brains to domain walls, from bubble universes to rotating time loops, remind us that even if our familiar universe seems smooth and edgeless, the deeper layers of reality might be far more intricate than our senses suggest. None of these ideas have been proven. They're like soft lanterns in the dark, illuminating the edges of imagination rather than the literal borders of space. But they help us understand something important. The universe doesn't owe us simplicity. It doesn't have to end where we expect it to. It might not end at all. Gödel's universe didn't come with physical edges, but it did something even stranger. It blurred the boundary between where space ends and where cause and effect begin to unravel. And that raises a question that feels almost mischievous, which is more unsettling discovering a literal wall at the edge of everything, or living in a cosmos where you could, at least on paper, bump into an earlier version of yourself before you start imagining round trip tickets to last Tuesday. It's worth saying that Gödel's rotating universe doesn't resemble the space we live in. Our cosmos shows no sign of the global spin his equations described, and the looping paths through time that solution allows remain mathematical curiosities, not travel plans. But the value of Gödel's idea isn't that it's true, it's that it teaches us something subtle. The universe isn't shaped by our intuition, it's shaped by the mathematics that govern space-time, and sometimes those equations permit realities far stranger than anything we'd write into a story. Another idea that stretches the mind is the holographic principle. Not holograms in the sci fi sense, no shimmering projections or glitchy illusions, but a deeply mathematical way of looking at reality. It suggests that everything unfolding inside our three-dimensional space, every particle, every force, every thought, could be encoded on a distant, two-dimensional boundary. The full richness of the universe packaged like information written on a cosmic surface, the way a hologram encodes a 3D image on a flat piece of film. This principle grows out of string theory and the physics of black holes, and while still speculative, it offers a mesmerizing possibility. Perhaps the ultimate edge of the universe isn't a physical border at all, but a place where information resides a boundary that defines the rules without behaving like a wall. All of these ideas share a deeper message. They're not telling us we'll one day reach a cosmic fence labeled End of Universe in bold block letters. Instead, they hint that boundaries may exist in forms we're not built to picture, edges woven into higher dimensions, limits baked into the physics of the early universe, constraints hidden in the way the information is stored at the deepest levels of reality. A boundary might not look like a cliff. It might look like a change in curvature, a shift in the laws of nature, a region where our familiar equations stop being familiar. And it's entirely possible that the universe has no boundary at all, no edge, no frontier, no outside. But even if space stretches on endlessly, we still run into limits, don't we? Limits of what we can observe, of what our instruments can capture, of what our minds can fully wrap around. Sometimes the edge isn't out there. It's built into our own perspective. Human beings evolved inside rooms and forests and coastlines. We expect things to end because everything around us does. So we bring that instinct with us when we look at the sky. We try to imagine the universe like a giant container with corners and sides. But the cosmos has never been required to follow the rules of houses or landscapes. It may curl quietly into itself. It may stretch endlessly in all directions. It may drift through dimensions we can't sense. Or it may have a shape so unfamiliar that we do not yet have the language to describe it. And yet we're here breathing, wondering, drifting through a universe that might not end anywhere. There's a calmness in that possibility, a soft reminder that maybe the cosmos is infinite, not just in size, but in creativity, not just in distance, but in potential, not just in what it contains, but in what it allows us to imagine, that even the questions themselves might stretch outward forever. It's already a lifetime's challenge just to grasp this one universe, its billions of galaxies, its spiraling black holes, its faint cosmic background, glow, its mysterious tendency to stretch, bend, and accelerate. We have more than enough wonders to keep the mind pleasantly occupied. And yet, every so often, physicists tilt their heads, squint at the equations, and ask an even bolder question: what if this universe isn't the whole story? Welcome to the idea of the multiverse, one of the most fascinating, most unsettling, and most deeply speculative possibilities in modern physics. At its core, it suggests something beautifully simple, that our universe may not be alone. There could be others, perhaps a handful, perhaps countless, each with its own rules, its own particles, its own version of reality, unfolding quietly beyond our reach. Entire universes where the constants of nature take different values, where gravity behaves differently, where stars form in stranger patterns, where history unfolds along alternate paths. maybe even universes where the decisions you didn't make still somehow happened. Before drifting too far into that cosmic dream, it's important to be clear. We have zero direct evidence for other universes. None. No faint signal from a neighbor cosmos, no shimmering doorway, no cosmic postcard that says greetings from universe number 27. The multiverse is not a scientific conclusion. It's a potential implication that emerges naturally from several well respected theories. It's a framework that helps us think about what might exist beyond what we can see, not a final answer. That said, the idea isn't just a sci fi indulgence. It shows up in multiple corners of physics, and each version has its own unique flavor. One of the gentlest to imagine is the cosmic multiverse, the bubble universe concept. This one arises from inflation theory, the incredibly rapid expansion thought to have happened right after the Big Bang. In this scenario, inflation doesn't turn off everywhere at the same time. Instead, it sputters, ending in some regions while continuing in others. Each region where it stops becomes a bubble of space, a universe with its own distinct physics. Our universe would be just one bubble in a vast froth expanding in parallel with countless others we will never meet. Picture a bathtub full of soapy foam. Each bubble is sealed off from the others, yet all of them exist within the same larger environment. That's more or less how this version of the multiverse imagines reality, a foam of universes, each drifting forever out of contact with its neighbors. Then there's the quantum multiverse, born from one particular interpretation of quantum mechanics, the many worlds view. In this picture, every time a quantum event has multiple possible outcomes, reality doesn't pick just one, it branches. All outcomes happen each in its own thread of the cosmic tapestry. Every choice, every chance event, every moment of uncertainty unfurls into a new version of the universe. In one branch, you hit the snooze button. In another, you got out of bed and made breakfast. In another, still something surprising happened. Something that feels like the kind of accident great discoveries are made of. The many worlds interpretation wasn't invented to be whimsical. It was developed to remove the mystery of wave function collapse and let the mathematics unfold cleanly. But it leaves us with an image of reality that is breathtakingly large. A branching tree of universes, each one as real as the next, each one forever inaccessible. There's no cosmic doorway to step between them, no gleaming station where travelers swap stories from alternate lives. These worlds remain separate, not because of distance, but because of the structure of quantum reality itself. And in at least one of those unimaginable branches, yes, there's almost certainly a version of you who made vastly different life choices, possibly even one where you're sporting a heroic mustache. Statistically, in a branching infinity, it'd be hard to avoid. Somewhere in one of those imagined realities, there's probably a version of you standing on a brightly lit stage, giving a full TED talk about alternate beard designs and their unexpected influence on neighboring timelines. And with that gentle laugh in mind, we drift into another branch of multiverse, thinking the mathematical multiverse proposed by cosmologist Max Tegmark. In his view, anything that can be described in a self consistent mathematical framework doesn't just exist as an idea, It exists as a physical reality somewhere, somehow. If a universe can be written down without contradiction, even one where pi takes on a different value, or where time loops gracefully, instead of flowing, then, in this interpretation, that universe is as valid as our own. It's a sweeping, audacious suggestion, one that edges close to philosophy, and it may forever sit beyond our ability to verify. But it's strangely comforting to imagine reality as an infinite library, each aisle lined with different mathematical blueprints, everyone describing a universe humming quietly in its own way. Of course, these multiverse concepts face real criticism, and they should. The biggest challenge is testability. If other universes are sealed off from us, forever unreachable by light gravity or information of any kind, how do we ever hope to probe them scientifically? How do you study a realm you can never interact with? Good science relies on predictions. We can check signals, we can measure, and theories we can refine. A cosmos filled with unreachable neighbors pushes hard against those boundaries. Some researchers see that as a red flag, a sign that certain theories may be wandering too far from the domain of experiment. Others think the multiverse is a helpful way to explain why our universe has the particular constants and physical laws it does. If countless universes exist, with countless combinations of parameters, then life naturally arises only in the few where the conditions happen to be just right. We're here not because the universe was tailor made for us, but because we simply show up in one of the universes where existence is possible, a kind of cosmic selection effect. It's like sitting at one table in a casino with infinitely many tables. Most of them roll nonsense, but at one table, purely by chance, the numbers align. That's the table we happen to occupy. Some cosmological models even suggest that collisions between bubble universes, if they ever happened, might leave faint scars in the cosmic microwave background. So far, no such imprint has been found, but scientists keep watching, listening, and refining their tools. Many great discoveries began as strange ideas that waited patiently for technology to catch up. In the end, whether the multiverse is real or not, thinking about it stretches our imagination in healthy ways. It encourages us to question our assumptions, to consider realities beyond the narrow slice we can see, and to remain humble in the face of the unknown. It reminds us that science is not only about building answers, but also about cultivating wonder. Even if this universe is the only one that truly exists, the very act of imagining others reveals something profound about our curiosity, that it can reach outward across time, across galaxies, and into concepts that may forever sit just beyond observation. And somewhere in some version of reality, whether metaphorical or literal, there's a version of you doing something fascinating, something brilliantly odd, perhaps even something involving a llama for reasons no one will ever fully understand. But here in this universe, you're sitting quietly, sipping your tea, or settling into bed, letting your mind drift over possibilities that stretch beyond the visible stars. And that simple moment, that quiet wondering, is its own kind of cosmic magic. And now here we are, returning gently to the question that started this entire journey. Where does space stop? It was a soft, innocent question, At the beginning, almost like a child asking whether the sky has an edge. And after drifting through expanding galaxies, curved geometries, ancient microwave glows, speculative boundaries, and universes stacked like invisible pages, we find ourselves looping back to the same mystery, still open, still shimmering, still inviting us to wonder. We've discovered that space doesn't behave like a hallway, a container, or a landscape with edges waiting to be reached. It isn't shaped like the rooms we live in, and it doesn't require a wall or a border to feel whole. The cosmos can be endless or limited, yet without boundaries. It can stretch, curl, wrap around itself, and evolve in forms our imagination is only beginning to catch up with. And it can even let distant galaxies drift away from us at speeds that appear to outpace light, not because they're racing through space, but because the fabric between us is quietly growing. We've also learned that our view of the universe is capped by an observational horizon, a limit defined not by walls, but by time itself. Beyond that horizon, light has simply not had enough years to arrive. What lies past that point is something no telescope can currently reveal. Perhaps the cosmos extends outward without end. Perhaps in some elegant geometric way, it curves back on itself in a direction we can never turn to see. Maybe our entire universe is a single bubble floating within an ocean of higher dimensions. Or maybe the multiverse is nothing more than a beautiful mathematical metaphor, a story we tell ourselves to explore possibility. What we can say with confidence is that space isn't an empty void. It's textured with structure, with fields with the soft residual glow of the Big Bang. It expands with time. It carries ancient starlight across unimaginable distances. It has no center, and from everything we can measure, no detectable boundary. And still the questions linger. Is the universe infinite or just astonishingly vast? Does its geometry curve gently or remain perfectly level? Is this reality a single island of existence, or one of countless worlds scattered through deeper layers of creation? And if space truly had an edge, what could possibly exist beyond it? These aren't failures of knowledge, they are signals that curiosity is still alive. The heart of science isn't certainty, it's the willingness to keep asking. Our exploration continues through equations, through silent observatories, through spacecraft listening for ancient photons, through the quiet thoughts that visit us in the middle of the night. Every measurement we take, every map we refine, every theory we adjust, brings us a little closer even when the horizon moves farther away with every discovery. Maybe that movement is the message. Maybe space doesn't stop because the mystery itself never stops. Maybe the cosmos doesn't need a final border to feel meaningful. Maybe its only requirement is to exist spreading softly outward, an open invitation rather than a locked door. At the very beginning, I asked you a few gentle questions: where you were listening from, what time it was, whether the idea of space having no end would keep your mind awake or help you drift into rest. My hope is that by this point, the edges of your thoughts have smoothed out a little, that your attention has settled into that calm, spacious part of yourself where curiosity and peace coexist. And if you're still awake, floating somewhere between focus and sleep, I hope knowing the answer isn't final, brings you comfort rather than worry, because that's what the universe offers us. Not just stars and silence, but the permission to wonder without needing to reach a conclusion. Perhaps space never truly ends, because the questions we ask were never meant to end either.